The last part of transient conduction is to use the graphical form of the series solution. Some of the in some of the cases the series solution can be truncated and the results for many situations are expressed in a graphical form. So, that gives a powerful tool for practicing engineers to find out what would be the temperature as a function of position. Remember this, in this case the Biot number is not less than 0.1 and therefore, the temperature is a function of the spatial coordinates, unlike the case where we have assumed that the temperature inside the solid remains a constant with respect to space, it only varies with time. But this is a case in which the temperature inside the solid can be a function both of space and of time. So, let us look at how it is done, and you should look at your textbook to see how the different charts or graphs are provided. I am only going to give you a brief introduction of those charts and how they are used to calculate through an example which will follow this lecture, through an example of how it can be used to obtain the temperature. So, these type of series solutions are commonly known as Heisler charts. So, this let us take a quick look at how we define this. So, we are looking at graphical representations of unsteady heat conduction. The result is the results are provided in graphical form, which is known as Heisler charts, and the graphical representations are valid for three of the most common cases of transient heat transfer, that is a plane wall of thickness twice L. It is also there for radial systems where R 0 is the radius of the wear, and it is also there for a spherical system where R 0 is the radius of the sphere. In all cases, T 0 is the centerline temperature. In these two cases, T 0 is the centerline temperature, that means the temperature along the axis, whereas for the case of a spherical system, T 0 simply refers to the center temperature. And all of these, the plane wall, the cylinder and the sphere, they are exposed to convection environment, which is let us say that the convection environment, the temperature is T infinity. So, as time progresses, based on the difference between the initial and the temperature to which it is exposed to, the temperature inside the solid will vary with time. Okay. So, we will say that at time, that is the initial temperature at time 0, T of the solid would simply be equal to a constant temperature T I, which is uniform throughout. So, this is uniform temperature. Initially, the temperature of each of these solids is at a constant value equal to T I, and the time varying temperature is given as T, which is a function of both x and time minus T infinity. So, this is some sort of a difference temperature. This is for a plane wall, whereas for the case of a cylinder, it is going to be T, which is which could be a function of the radius, the radial position and time. So, this is what we have for theta, and this theta I, which is the initial temperature difference, is T I minus T infinity, and finally, what we have as theta 0 to be equals T 0 minus T infinity. So, one more time, here we see that the temperature is a function of location as well as time. So, theta, the difference temperature, denotes T as a function of x and T minus T infinity for the case of plane wall, whereas for the case of cylinders or spheres, this theta is simply T R T minus T infinity. So, for the case of a cylinder, this is simply the centerline temperature different as compared to the T infinity, and for the case of sphere, it is the center temperature with center temperature or at the center temperature with respect to T infinity. So, theta I is T I minus T infinity. The solid object could be hotter or cooler. So, that is what is related over here, and theta naught, which is the centerline temperature minus T infinity. So, I guess the three nomenclature of theta, theta I and theta 0 are clear. Theta is the temperature as compared to T infinity, theta I is the initial temperature as compared to T infinity, and theta 0 is the centerline temperature in comparison to T infinity. So, the results of this, the results of this are expressed in graphical form, and I will show you one or two of representative graphs how they look like. So, let us think about let us take the plane walls. You in your text you would see that this theta 0 by theta I, this is the centerline temperature and this is the initial temperature. They are plotted as a function of Fourier number between 0 to 1. So, at t equal to 0, that is at this point, the theta 0 must be equal to theta I. So, all points in the solid will be at a constant temperature at time t equals 0. As the time progresses, you are going to get a family of curves like this. So, this value is roughly about 0.2, up to 0.2 it has been done, and this is increasing value of the inverse of Biot number. Okay. So, this is one figure which is provided in the text. So, this essentially gives you the theta 0, which is the mid plane temperature for an infinite plate of thickness 2L. So, what I mean by infinite thickness is that the plate is really wide, however, its thickness is finite and that thickness is equal to 2L. So, this curve provides you with what is the centerline temperature, how does the centerline temperature vary with time for different values of Biot number. So, having this graph for the plane wall would let you find out what is the centerline temperature as a function of time. Okay. But you need definitely you need the centerline temperature, but you also need the temperature at every point in between. So, what is to be done if you require not just the centerline temperature, but the temperature at every point in between. So, for that there is a second curve. So, which you can also see in your text, but I am going to draw it over here, so that we know what these curves look like and how to use those curves for calculating the variation in temperature. So, what it look like is the curve is plotted as a function of k by h l and theta by theta 0, again from 0 to 1, in roughly they would look something like this. So, this is x by L equals 1 and this is x by L equals 0.2 and some points and in between. So, this gives temperature as a function of center temperatures or central line temperature in this case, in an infinite plate of thickness 2L. So, again if you look carefully and just to remind you, I write the expression, I write what are theta as T x t minus T infinity or T r t minus T infinity, theta naught is T I minus T infinity and theta I, and theta naught to be equals T 0 minus T infinity. So, let us say you would like to find out, and these are for plane walls. All the two curves that you see are for plane wall, and in your text you would see the similar curves are there for the case of spheres as well as cylinders. So, let us say you would like to find out what is going to be the temperature of a plane wall which is experiencing convective heat loss or gain from two sides. The thickness of the plate is twice L and it is really wide in other directions. So, how do you find the temperature knowing that lumped capacitance model cannot be used? So, use Heisler chart. The first Heisler chart where the x axis is going to be Fourier number. So, if you look over here, the x axis is Fourier number which contains the time, and the y axis is the center line temperature. So, for different values of Biot number, or rather inverse of Biot number, so what you need to do is first find out what is the Biot number for your system. It is greater than 0.1, but you still you exactly know what is the value of Biot number, and find out what is the value of Fourier number after, what is the value of Fourier number corresponding to the time that you at which you would require the temperature. So, let us say t equals 10 minutes, you know the value of alpha, you know the characteristic length. So, you know the value of Fourier number. You go all the way up to the Biot number which relates to your material, and then come to this side, find out what is the value of theta 0. The theta 0 is nothing but T 0. You understand that this T 0 is also a function of time, whereas T infinity remains constant. This T I, the initial temperature, is not a function of time. So, therefore, this has a fixed value. So, in this theta 0 is a function of time. So, through the use of this curve at a given t for a given value of Biot number or inverse of Biot number, you find out how the center line temperature is changing with time. Then you come to curve 2. In curve 2, again you see that inverse of Biot number is there in the x axis, and the family of curves that you see are at different locations in the solid. X by L to be equal to 1 refers to this point, whereas x by L to be 0 refers to the center line. Thus, if you want to find out what is the value of temperature at, let us say, at a point exactly midpoint between these two planes right over here, that means x by L equal to 0.5. So, from the value of inverse of Biot number, you go all the way up to x by L equals 0.5, come to this side and find out what is theta by theta 0. What is theta? Is the temperature. What is theta 0? You have already obtained from curve 1. So, in order to obtain the center line temperature, you require just one curve, one chart. In order to evaluate the temperature at points in between the center line and the surface, you require this curve as well, where from the value of the inverse of Biot number, you go to the curve corresponding to the location, corresponding to the dimensionless location, and read what is the value of theta by theta 0. Since theta 0 is known, theta can be found out. So, this is the way by which one can obtain for simple geometries, plane wall, cylinders or spheres, what would be the value of temperature as a function of position and as a function of time. All these are valid for Biot number Biot number greater than 0.1, where the lumped capacitance model is not valid. Now, there is a second part to it, which in some cases you are not only interested in to know what is the temperature, but you would also like to know how much of heat the control volume, let us say the sphere, has gained while it is being heated. How much heat is gained by a cylinder while it is being heated, or if it is being cooled, how much of heat it has lost. Since the temperature is not space wise isothermal, you would exactly like to know what is the energy content of the body at a given instant of time. And that brings us to the third figure of a third chart of Heisler chart, which will give us the value of the energy content of the object as a function of time. So, the first two charts are to find out what is the centerline temperature and what is the temperature at any point in the control volume. The third chart of Heisler, the third figure of Heisler chart refers to how much energy, what is the energy content of the body as a function of time. So, I will draw that, and which will complete our study of transient conduction. So, the curve looks something like this. This is Q by Q naught from 0 to 1. It looks something like this. So, this is h square alpha t by k square, which is nothing but Fourier number times Biot number square, and these are h L by k. So, this Q is the heat, let us say it's a quenching problem. So, heat losses, this Q refers to heat losses for the infinite plane, infinite plate or infinite cylinder and infinite sphere. And Q 0 is the initial internal energy of the body. We know that initially the entire object is at a temperature of Ti, which is same everywhere, which is a constant. So, Q 0 can be written as rho C V T I, which is the initial temperature minus T infinity, nothing but rho C V theta I. Okay. So, in this figure, Q is the actual heat loss or gained, depending on whether it is a heating problem or a cooling problem, by the body in time t. So, if you know what is the time if you know all the thermophysical properties, essentially if you know the Fourier number and the Biot number, then using these graphs, using these curves corresponding to different values of Biot number, you should be able to calculate what is Q, since your Q naught is known to you. So, since you know the initial internal energy content of the object, you would be able to find out what is the energy that the body has lost if it is a quenching problem, or the body has gained if it is a problem where the object is going to be heated. That means, it is exposed to a convection environment where the temperature is more than that of the object itself. So, through this chart, you then would be able to calculate the total amount of energy gained or lost in the system. So, this is the third Heisler chart which can be used for many of the engineering calculations, provided you are dealing with a plane wall, or you are dealing with an infinite cylinder, or you are dealing with a sphere. Okay. But there is one word of caution here: this truncation of the infinite series solution which has been used to obtain these or to generate these curves has a limitation. It is only valid when the necessary condition for Heisler chart to be valid is that Fourier number, which is defined as alpha t by L square, must be greater than 0.2, where this L is the characteristic dimension. So, this condition has to be kept in mind while using the Heisler chart for calculating the energy, calculating the centerline temperature, or calculating the temperature at any point in between the center and the surface of the object. So, this is another useful and compact way of finding out what is going to be the temperature for situations where lumped capacitance model cannot be used. I will quickly give you a problem for you to practice. So, that is going to be another tutorial problem, but I will not solve it completely in the class. You try it on your own, and if there is any question, I will discuss it or the TAs will discuss it with you for the solution. So, the problem that we are going to deal with is this, a problem on transient conduction again. So, you consider a steel pipeline which is 1 meter in diameter. So, you have a pipeline whose has a wall thickness of 40 millimeters. So, this length is 40 millimeters, and it's heavily insulated on the outside. So, this side is insulated. Then the pipe is before the initiation of the flow, the walls of the pipe are at a uniform temperature of 20 degrees centigrade. So, what we have initially is that T at any x but 0 time is equal to T I equal to minus 20 degrees centigrade, and then you have hot oil which is pumped through this pipe at with a convective heat transfer coefficient corresponding to H equals 500. So, H is equal to 500 watt per meter square at the inner surface. Now, you have to find out what is going to be the appropriate Biot and the Fourier numbers 8 minutes after you start the flow of the hot oil. So, initially everything was at a temperature of minus 20, and then suddenly you start passing current passing a hot oil through this, and you would like to find out how the temperature will change at different points. So, what we can do then is, first of all, to calculate the Biot number, after t equals 8 minutes. So, when you go for t equals 8 minute, the Biot number is HL by K, and by putting the values in there, you would see that Biot number is equal to 0.313. So, it is definitely greater than 0.1. So, LC is not valid. So, that is one observation, and you can also obtain the value of Fourier number, and you should check yourself that if this is going to come to 5.64. So, this is the first part of the problem. The second part of the problem, it says, is after t equals 8 minutes, what is the temperature of the exterior pipe surface covered by the insulation? That means, what is the temperature of this surface after 8 minutes? Now, the interesting thing, that what you need to realize or need to see is that this is exactly like half of a pipe of thickness 2L. Now, if you remember what happens at x equal to 0, that means at the center plane of the center plane of the system, planar system, it acts like an adiabatic wall. The temperature is maximum at that point, and therefore, x equals 0, from x 0 to L is identical at from x 0 to minus L. So, having the pipe insulated at x equal to 0 ensures that I can use the solution of the plane wall for this case as well. So, in the outside of the pipe wall, this is nothing but the centerline temperature of Heisler chart. So, we are only looking at half of this, we are only looking at this part which is over here. So, since this is an adiabatic plane and this is an insulated plane, this part and this part are identical, and therefore, Heisler chart is going to be valid. So, that part 2 is part 2 of this is what is going to be the temperature of the exterior pipe surface. So, this, if you need to find that out, then what you need to do is you are going to use Heisler chart, and for a Biot number, inverse of Biot number to be equal to 3.2, you find out what is theta 0 by theta I from Heisler chart. So, what do you have? This here is essentially you are using the first curve. So, for t equals 8 minutes, that means you are calculating the value of Fourier number, you know the Biot number, you go all the way up to the value of Biot number, corresponding Biot number for this plane wall, come to this side and find out what is the value of theta 0, where theta 0 is nothing but the centerline temperature minus T infinity. So, with this from Heisler chart number 1, you should be able to calculate this theta 0 by theta I to be equal to 0.22, which would give you the centerline temperature at t equals 8 minutes to be equal to 42 degree centigrade. The third part of this problem asks you what is the heat transfer to the inner surface. By inner surface I mean this surface. What is the heat flux to the pipe from the oil at 8 minutes? So, how much of heat gets transferred from the oil to the pipe? So, that's essentially the problem. The temperature of the hot oil, which I think is not mentioned over here, the temperature of the oil is at 60 degree. So, hot oil, T of the oil is 60 degree, which is missing here, 60 degree centigrade. So, when it says what is the heat flux to the pipe from the oil at 8, it equals 8 minutes, then I am essentially trying to find out, if I can find out what is the temperature at x equals L and t equals 8 minutes. If I can find this, then the heat flux would simply be equal to, the heat flux would simply at x equals L, it will simply be equal to H times temperature at x equals L at 8 minutes minus T infinity, where T infinity is that of the oil. So, this is 60, this is provided as 500. Now, we have to find this. How do you find this? In order to find the temperature at x equal to L, what you need to do is use the second chart. In the second chart, you know what is the inverse of Biot number. You go all the way x by L to be equal to 1, x by L to be equal to 1, and read what is the value of the x axis. So, here theta by theta naught you have already calculated from here. So, you can calculate theta, which is corresponding to x equals L. So, this value would give you the temperature of the inner wall of the pipe after at a time equals to 8 minutes. So, when you use Heisler chart 2, number 2, you should be able to find out, you should be able to see that your theta at L corresponding to a time of 8 minutes, which is 480 seconds, by theta naught to be equal to 0.86, which would give as T L 480 to be 45 degree centigrade, and therefore, Q double prime L would be 500 times 45 minus 60 equals minus 7500 watt per meter square. So, that means this much of heat flux Q double prime is going to come from the oil to the inner surface at 8 minutes, after 8 minutes. So, since with increase in temperature, with increase in time, the temperature of the wall will also increase, therefore, the amount of heat which would get transferred from the hot oil to the cold wall will decrease with time. It is going to be a function of time, and in order to obtain the value of the heat flux at any specific instant of time, you need Heisler chart 2. But in order to use Heisler chart 2, you should first calculate from Heisler chart 1 what is the centerline temperature, because the temperature at any point in the solid will be given as a function, is going to be non-dimensionalized by Q naught, which is the centerline temperature. So, when you do that, you are going to see that this value of Q double prime would come out to be 7500. And the third part of the, or the at the last part is how much of energy has been transferred from the oil to the pipe in 8 minutes. So, the last part is you have to find out what is the value of Q till 8 minutes. What is the value of heat that has been transferred from the hot oil to the pipe over the time period of 8 minutes. So, obviously, here you are going to use the fourth chart, the third chart, where this is the amount of heat which has been transferred, this is the amount of heat which was initially contained in the solid wall, and here you have the Fourier number which contains time and Biot number square. So, at time equal to 8 minutes or 480 seconds, you calculate this one, you go all the way up to the Biot number, to the curve corresponding to the Biot number in this specific case, come over here and find the value of Q by Q naught. When you do that for this specific problem, you would see that for a Biot number of the present system to be equal to 0.313 and Biot number square times Fourier number equal to 0.55, your Q by Q naught from the curve you will read as 0.78. So, your Q is 0.78 Q naught, and your this should be Q naught should be equal to rho C V T I minus T infinity. So, this Q then is 0.78 rho C, and V is pi d times L. So, this T I minus T infinity. So, this is the volume is pi d L, where L is the thickness of the pipe times length of the pipe. So, when you do this, this is Q prime, and Q prime is simply Q by length of the pipe, and when you put the numbers, you would see Q prime to be equal to minus 2.7 into 10 to the power 7 joule per meter. The minus sign in the total amount of heat that is transferred from the oil to the pipe, or the minus sign what you would get, that heat transfer, the heat flux from the oil to the pipe simply refers to that the heat travels in the direction of minus x. Okay. So, the only significance of the minus sign is the direction of heat transfer. So, now at the end what we have in transient conduction is that we know there are two principal methods for solving transient conduction problems. One is the lumped capacitance, which is easy to use, which gives us a compact form, but it has certain limitations. It can only be used if the value of Biot number, which is conduction resistance by convection resistance, if it is less than 0.1. And we have solved a problem, in fact a number of problems, to see how it can be done. The second one is when the lumped capacitance model cannot be used, what is the alternative? The alternatives are either go for an analytic solution, go for a numerical solution, or in some cases the series solution arising out of the analytical solution, they have been presented in the form of curves for geometries like pipe, the plane wall, the cylinder, or the sphere, and these charts can be successfully and effectively used to obtain not only the centerline temperature, but temperature at any point in between. Apart from that, the Heisler chart can also be used to find out what is the total amount of energy transferred from the object to the outside ambient, or vice versa, and as a function of the initial energy content of the object. So, the third Heisler chart presents in the x axis, what you get is Q, the total amount of energy transfer, divided by Q naught, where Q naught is the energy content, and the x axis contains both time and the length scale thermophysical property, all combinations, by having Fourier number times Biot number square. So, through the use of all three curves, one would be able to obtain what is the temperature and what is the energy that gets transferred over a certain period of time for a specific solid, for a specific convective heat transfer coefficient, and so on. So, in the last class on conduction heat transfer, we will look into something interesting, some interesting applications of conduction heat transfer to reduce the temperature or to increase the heat dissipation from some specific systems. We are talking about fins, what fins are, what extended surface are, what are their applications, and when we can prescribe the use of fins to increase the heat transfer from an hot object. So, that would be the last topic in conduction heat transfer, and then we will move to convective heat transfer from the next to next class.